Now, let us discuss lesson number 7, Evidences of Evolution. For our objectives, we have describe the evidences to support evolution, explain some modern evidences of evolution, and show sensitivity to the importance of studying the evidence of evolution. Four major categories of evidence for evolution: fossil evidence, anatomical evidence, embryological evidence, and biochemical evidence. Let's look at fossil evidence first. Fossils are often used as evidence for evolution. They are the traces or remains of dead organisms that lived long ago. Sedimentary rock contains the most fossils and is formed from mud, sand, silt, and other fine particles. To make a fossil, first, the animal needs to die and be quickly buried under the mud or silt so that no other creatures will be able to break down the dead animal. Over time, the minerals in the mud and silt will replace the tissue of the animal and will later reveal a mold or cast of the long-dead organism. The law of superposition is that older layers are on the bottom and younger layers of rock are on top. This allows us to relatively figure out the age of different organisms or fossils that we find in layers of rock. So, an organism found below another organism would be older than the one on top. So, letter Z is older than letter X in this case. Absolute dating places a numerical age range using radiometric dating, luminescence dating, dendrochronology, and amino acid dating. Some scientists prefer not to call it absolute, but chronometric or calendar dating instead, because the word absolute makes it much sound more certain and precise than it really is. It is still an estimation, like the relative dating of rocks based on the law of superposition, but it has a number to it. For example, in dendrochronology, scientists count the rings in a tree to estimate the numbers of years that have gone by. Differences in growth through the season create a ring, and it generally takes 1 year, but there can be some variation. Transitional species are intermediate species which may be in the fossil record or could be missing from the fossil record. It's proposed that there would be evidence of species that were in the middle evolution steps from one species to another. Archaeopteryx, pictured here, is used to provide a link between the theory that birds evolved from reptiles. Now, we are going to start looking at the anatomic evidence for evolution. Homologous structure helps scientists find relatedness among species. There are anatomical structures in different species that originated by heredity from structure in the most recent common ancestor of the species. For example, if you look at the bone of pterodactyl, a bat, and a bird, you will see some basic similarities. This suggests that they had a common ancestor with a similar forearm structure perhaps very long ago. But if you look how they use their forearms for flight, they're very different. The pterodactyl has one long finger that spans a large section of the wing. The bat has a wing between its fingers and bird has a long feathers all along the forearm. These are analogous structure because even they have closely related functions, they do not have common ancestor for that functions. Each of these species evolved their ability to fly from different ancestral lines. Vestigial structures, another piece of evidence because the structures seem to serve no function but resemble structure with functions rolled in the organism. An example that is commonly used is the human appendix. The appendix was thought to be shrunken remain of cecum that can be found in many kinds of herbivores. The idea is that it's a remnant of evolution yet to be truly removed. In 2013, however, scientists refuted the relationship between cecum size and appendix presence. The appendix is actually a housing complex for mutualistic bacteria that aid in digestion for many species including humans. Embryology is the study of development of embryos. The more closely related species would be similar in the earliest stage of development. These exaggerated drawings by Ernst Haeckel were used to show similarities between early stages of an embryo among different species, including salamanders, pigs, and humans. And while they are not truly accurate, there were some of the first attempts of using embryology as evidence for evolution. Today, the stages are studied at the same point of their evolution, unlike these images. Lastly, when we read DNA in amino acids to find quantitative way to organize evolutionary ancestry, we are using a molecular clock. Mutations happen at a steady rate, and the more mutations there are, mean a more distant relationship between the species. Fewer mutations mean a more recent common ancestor. So, based on the amino acid differences between human hemoglobin and gorilla hemoglobin, gorillas are the closest relative to humans on this list, and lampreys are the farthest. And that's it for lesson number 7. Thank you for watching.